welcome to my classroom. Today, we're going to be talking about a unit created for chemists by chemists. Now, when I say unit, you use units in your everyday life all the time. When you're at Starbucks ordering your drink or your local fast food restaurant, you don't say, I'll have 32 ounces of soda or 16 ounces of coffee. You say, maybe I want a small, medium, or large. Same thing when you're going to buy a shirt or a hoodie at your local store. You're not going to say that I want a shirt that's 23 centimeters long, 13 centimeters wide. I hope that shirt's not it. That's an awfully small shirt. You would say that I want a small, medium, large, extra large, and so on and so forth. These sizes are created by us to help us quickly assess how large something is. We also do this in quantities. So when somebody asks you to pick up a pair of shoes, well, you automatically know a pair is 2. We also might say, go pick up a dozen donuts. Well, that means 12. Or if you're picking up a ream of paper for your office, that's 500 sheets. All of these units are created so that we can quickly assess how many or how big something is. The same thing happens in chemistry. Instead of us walking around and saying, well, I've got 10 grams of water in my hand, we use our own unit. It's called the mole. This unit is so that we can easily convert and understand and quickly assess how much we have of something. Now, let's see how it works. We're going to start this lesson off with a question. I have a sample here of plain sugar. And my question for you is how many oxygen atoms are in this sample of sugar? In order to answer this question, we're going to need to be able to perform calculations that allow us to go from the macroscopic view, the sugar, to the atomic level. And in order to do that, we need to use that unit, the mole. Now, how do we use the unit of the mole to move from the macroscopic to the atomic level? Well, in order to do that, in terms of macroscopic, we're talking about mass. Now, to go from mass to mole, we need to use the connection piece. The connection piece is molar mass. Now, we don't yet know what molar mass is, but that's okay. In order to figure that out, we need to look at a periodic table. So let's take, for example, the element copper. If I look at the periodic table, which we're not exactly familiar with just yet, we're going to learn more about the what it can provide us, and we're going to learn one more thing today. On the periodic table, it tells us a lot of information. 29, the atomic number, the elemental symbol, and the element. This number below here, this is the molar mass. So if I look at the periodic table, I can read the molar mass of copper. It's 63.546 grams per mole. Now, what do I mean by grams per mole? Well, I have some copper here. This copper here, some copper pipes, is 1 mole of copper, which means that if I mass this out, I should get that the mass is pretty close to 63.546. Now, I also have another example. Let's say zinc. Well, if I had a mole of zinc, that would weigh roughly or have a mass of roughly 65.38, which I do. So I have some hardware. Went to the hardware store to pick up. This is roughly 1 mole of zinc, meaning that if I mass this out, I would get 65.38. Let's try this again. I was able to pick up some aluminum. Now, aluminum here, I don't have exactly a mole. I have a half a mole. And my question to you is, if I have a half a mole of aluminum, how much aluminum would I mass out? Well, you should guess it's about 1/2 of this number. So roughly 13.5-ish grams. Same thing if I had nickel. I wasn't able to acquire a full mole of nickel, but that's okay. I have about this much, which is 0.1 moles. Now the question is, if I mass this out, how much would I mass? Well, I would have 0.1 of this, which would be roughly around a little less than 6 grams. That is what molar mass is. I took these masses and converted them to moles. Now you're doing them in your head with me, but I'm going to show you how to do it in an example. Now this is also helpful for molar masses of elements, but what happens when we need to calculate the molar mass of a compound? So let's get rid of these examples for a second. Sorry for the noise. And look at an example of a compound. One that we're used to quite often, NaCl. This is sodium chloride. Sodium chloride is table salt. It's composed of sodium and chlorine. Now, in order to figure out the molar mass of the compound, I have to add up the molar mass of the individual elements. So in this case, there is 1 sodium atom in a molecule of sodium chloride. Well, the molar mass of sodium is 22.990. I got that from the periodic table. Since there's only 1 atom of sodium per molecule, compound, or formula unit because it's a metal and a nonmetal here, that means that the mass contributed by sodium is 22.990 grams per mole. Now, chlorine, on the other hand, there is still one of them, but the mass is different. It's 35.45 grams per mole, which means that if I had 1 mole, chlorine contributes 35.45 grams. In order to figure out the molar mass, I just need to add the mass that each of them have together. And I get that the total molar mass of sodium chloride is 58.44 grams per mole. That's it. So the molar mass of an element is read directly off of the periodic table. The molar mass of sodium, 22.990. In order to find the molar mass of a compound, molecule, or formula unit, I need to add them together. Now, molar mass can get a little more complicated. Let's try a harder molecule. Let's look at a hydrate compound. This compound is copper sulfate pentahydrate. A lot more going on than just that sample of sodium chloride. Now here, you can see that it's a hydrate, which means that it's surrounded by water molecules. So copper sulfate is surrounded by 5 water molecules. That's okay. We can still calculate the molar mass. Let's break it into the steps similar to what we did with sodium chloride. First, sulfur. Well, sulfur has a molar mass of 32.06 from the periodic table. There is one of them. So my mass of sulfur is 32.06. Copper, which we just looked at, has a molar mass of 63.546. There's one of them. So that means my total mass for copper is 63.546. Now, oxygen and hydrogen are a little more complicated. Oxygen, there's not just one. There are several. Now, you can figure out how many oxygen by looking at the molecule here and counting them, or you can use the subscripts. So if I use the subscripts, which is easier, I can see that there are 4 oxygens here, and then there's 1 for every water molecule. Well, there are 5 water molecules, so that's 5 for the waters, 4 for the compound, which means that there should be a total of 9 oxygens. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 oxygens, which means that when I calculate the molar mass contributed, I need to multiply it by how many there are. Well, there are 9 times 15.99, so the mass contributed by oxygen is 143.9991 grams per mole. Same thing for hydrogen. If I look at hydrogen, it's only contributed by the water. Well, every water molecule has 2, so there's 10 total hydrogens. So 10 times 1.008, that gives me 10.08 grams per mole is contributed by hydrogen. In order to determine the molar mass, then, I just add all those numbers up. And I get that the molar mass of this compound is 249.677 grams per mole. That's molar mass. And that's awfully a complicated problem in order to understand how it works. Make sure that if your formula has parentheses, that you distribute that subscript to each of the elements in terms of calculating that molar mass. Great work. Now we understand how to calculate molar mass. That provides us a little more insight into how we go from this macroscopic view to an atomic view. So let's go back to that illustration of the mole. So I have the mole, right? It's connected by mass. Mass to mole, I use molar mass. Now that's not yet on a macroscopic view. I need to get, or an atomic view. I need to get down to the molecule level or molecular level. That's the next branch. In order to go to a representative particle, meaning it could be a molecule, 2 nonmetals, a formula unit, a metal and a nonmetal. In order to get there, I need to use Avogadro's number. Now, Avogadro's number is a constant. It's a number we've created because that's based on the mole. We'll get more of where that number came from later, and feel free to ask and we'd be happy to explain. Avogadro's number, 6.022 times 10 to the 23rd, that is a big number. So you can think about it as 6022 with 20 zeros following it. That is huge, but remember, we're going from the macroscopic to the atomic level. Things are much tinier, that's why there's so many more of them. Check out, for example, this scale. I want to use this scale to help illustrate why Avogadro's number is so large. So remember, we're trying to move from the macroscopic to the atomic level. And here you can see the largest element is 3.96 meters. So we're on the meter level. Now, as I zoom in here, we're going to try to find and see how small do I have to get to an atom. So if I pay attention to some of the things that I'm passing, a penny, cent, rice grains, sand, and now look, I'm getting to structures. And I'm still going smaller and smaller. I have viruses. I have wavelengths now popping up. And here, look, I have molecular structures, ATP, glucose, still getting smaller to here, to the hydrogen atom, helium atom, and the carbon atom. You can see that they're roughly in the picometer range. Now, if you look in the bottom right-hand corner, you see that a pico is close to 10 to the 11th power down here. That is really small compared to the size of the elephant that we started with at 10 to the 0. So that's why Avogadro's number is so enormous, because the amount of atoms contained within objects is huge merely because they're so tiny. Now you can see why this number is so large. It's because those items are so small compared to what we're actually dealing with, which is why we use a mole. A mole is much easier to state than 6.02 times 10 to the 23rd. You don't see chemists running around saying, oh my gosh, I've got 6.022 times 10 to the 23rd atoms of oxygen. No, they're going to say I have a mole of oxygen atoms. But we'll get to that a little bit later. Now, how do I go from representative particle to this atoms? Because that was my question. I have another step. I need to use the subscripts on the formula unit. If I can get to molecules, then I just have to figure out how many atoms are in each molecule in order to get to atoms. Let's work an example that we started with. We started by asking this sample of sugar, how many oxygen atoms are there? Now, you don't know this, but sugar, that chemical formula is sucrose, meaning C12H22O11. Now, my question is, how many oxygen atoms? In order to do this, we have to use that same conversion, that full mole conversion. We're starting with a mass. I measured it. It's 109.18 grams. We're starting at mass. We're going to need to be able to go to moles. Then we're going to need to go to particles. And then we're going to need to go to atoms. This is a lot of steps to get that answer, but that's okay. It's going to follow the same method we've been using in dimensional analysis to get there. Same process, different relationships. So let's try it out. So I know that there's 109.18 grams of sugar or sucrose in this problem. Now I need to calculate the molar mass of sucrose. In order to do that, remember, the molar mass is the element, so in this case carbon 12.011 times 12, because there are 12 of them, hydrogen 1.008 times 22, plus the oxygens contributed. The oxygen in this case is 15.999 times 11. I add that all up to get the molar mass, and that's my first step. So if I set up my dimensional analysis correctly, I should have 109 grams. Now I need to convert to moles. Now we need that molar mass that we just calculated. Well, that molar mass is 342.297 grams. Now remember, in dimensional analysis, we multiply by what we want over what we have. I have grams, I want moles. So my molar mass is 1 mole is 342.297 grams. If I had it reverted, if I had moles, I would flip this because then I would want grams, right? My next step is I need to go to molecules. This is Avogadro's number. Well, every mole has 6.022 times 10 to the 23rd molecules in it. In this case, it's a molecule. It is all nonmetals. That's the step. So now I know how many sucrose are in this, if I do this math, are in here. The question, though, is how many oxygen atoms are in the actual sample? This is what gets students caught up. Well, think about it. If I have this many, I already know how many of these I have. Well, every one of these has 11 oxygens. So I need to multiply this number by 11, which is where I get my last conversion. That 11 oxygen atoms are in one molecule. And if I do my math and record to the correct number of significant figures, you should get that there are 2.1129 times 10 to the 24th oxygen atoms in this sample of sugar. Now, the next time your mom asks you or your parent or guardian asks you to grab a half a cup of sugar, you can say, well, I'm going to grab 2.11 times 10 to the 24th oxygen atoms. Excellent work, Velociraptors. Now, hopefully you can see this unit created by chemists known as the mole helps to connect quantitatively the macroscopic and the microscopic or atomic world so that we can better assess how many atoms, how many molecules, how much mass an individual substance contains. This helps us to quickly do mathematical calculations and soon will help us predict how much product and how much reactant we need. Thanks for tuning in.